Alright, so this problem is asking us to find the length of a curve given by a parametric function. The formula is written in orange, and pretty much for these problems it's just computing the derivatives and then doing some simplifications. There's pretty much two cases that occur a lot, is that either the inside of the root becomes some term squared and then the square and the square root cancel, or you can factor something out of it, out of both of the dx dt squared and the dy dt squared, and then create a u substitution. So I guess we're going to see what case this is in a second. So let's just start off by taking those derivatives that we're going to need. So dx dt is equal to 6t, and then dy dt is equal to 6t squared. So it looks to me like this is the case where you factor something out just because they're very similar. So then let's actually plug it into the formula. And then alpha and beta are just the t values they give you that it's bounded between, so 0 and 1. And then, okay, so dx dt squared is 36t squared. And then dy dt squared is 36t to the 4th. And then we still have our root dt. And then to simplify this, we can see that they have some common factors. So let's pull some stuff out. 0 to 1, let's pull out. I'm going to do it in two steps. 36t squared out of both of them. dt. And then from there, well, this portion, the product of roots can be separated, right? So then we could just write that as 0 to 1 root 36t squared times 1 plus t squared dt. And then we're left with 0 to 1, 6t, when this is a perfect square, square root 1 plus t squared dt. So this is the case where it amounts to a u substitution, and you can pull something out because we have a t squared in here, and the derivative of t squared minus the coefficient or whatever is t. So let's actually do that. Let's do our u substitution. So let's say u is equal to 1 plus t squared, and then du, so the inside of the radical is a good thing to make the u, and its derivative is appearing outside, so double check there. And the derivative of that is just 2t dt, and I personally like writing it separating the dt, so dt is equal to du over 2t. Okay, and the last thing I guess we should do is probably find our bounds of u, or limits of integration, because those are t values. So when doing a u sub, unless you want to plug in this expression at the end for u, you do want to change the limits of integration. So let's do that. Let's just call u1 and u2 is fine. So u2, so that's when I plug in 1, we get 2, and u1, when I plug in 0, we'd get 1. So this integral is just going from 1 to 2 now instead of 0 to 1. And then, alright, so what did we have? We had 6t root u du over, oops, this should be a t, 2t. This is just replacing our dt with this expression, and then that's just subbing in our u. Okay, so these t's cancel. That's good. We're just in the u world now, and we're left with a factor of 3, the 6 over 2. And then we're going from 1 to 2 of root u du. Alright, running out of room here. So the 1/2 we add. So we got 3/2 and then a 2/3. So hopefully it's not too many steps. And then let's see, 2 times, and then 2 to the 3/2. Well, that's root 8. So 2 root 2. And then I factored out the 2 here. So it's just really the 1 minus 1. And then if you wanted to write that as final answer, factoring the 2 back in, we get 4 root 2 minus 2 as the final answer. Alright, so that's how you find the length of a parametric curve. It's really just taking derivatives, and then the hardest part generally is once you do that, how do you simplify into a way that you know how to integrate? And it usually amounts to U substitution or something like this, right, where you have a term squared under the root and they just cancel, and then you can integrate each of those individually. So those are the cases. Yeah.